So the problem we have today is to find the shape of the most economical cylindrical can. Now this is a vague problem, and I think it's a deliberately vague problem. There are at least a couple of ways of thinking about it. We could ask ourselves, first, given a fixed volume, how do we minimize the surface area of the can? Or second, given a fixed surface area, how do we maximize the volume of the can? In both cases, what we're optimizing is something which, when optimized, will hopefully make the can the most economical by using the fewest resources. So let's pick the first approach. And we'll use the second approach to check our first approach. So we're going to answer the problem given a fixed volume, let's say V. What is the minimum, given a fixed volume V, we're going to minimize the surface area. Let's call it S of a cylindrical can. Okay. Now, what is the surface area? Let me begin just by drawing a picture. So here's our cylindrical can. Let's say it's of radius R and of height H. So in this particular case, the surface area, the thing we want to minimize, consists of three parts. We have a circle at the top and a circle at the bottom. So we have two shapes of area pi r squared. And then we have the outside of the can. So you can imagine that if you cut down the side of the can and you unfold it, you get this rectangle whose height is h and whose length is the circumference of the circle, namely 2 pi r. So this is the thing we want to minimize. Now the problem is we want to adjust the radius of the height, r and h, in order to minimize this. But we only know how to minimize functions, at the moment anyway, of one variable. And so my next task is to reduce this function from being of two variables to being of one variable. I do this by looking at the constraint. We know that this can has to have a volume V. So we know that pi r squared h, which is the volume of a can, has to be equal to this constant V. So what I'm going to do is I'm going to use this constraint to solve for one of my variables, and then I'm going to plug it back into this equation in order to get a function of one variable rather than two. Now I could solve for r, but instead I'm going to solve for h because solving for r is going to entail taking the square root of something, and I don't want to do that. So we know that V is equal to pi r squared h. In other words, h is equal to V over pi r squared. So we can take our function s and write it as a function purely of r. So s of r equals 2 pi r squared, which is this term here, plus 2 pi r, and now I replace the h with this term, V over pi r squared. And this is the function that I'm going to play with. This is now a function that is vulnerable to our usual techniques. I can sketch the graph of this function if I wanted to. But what am I interested in? I'm interested in finding the value of r that minimizes s. So what I'm going to do is I'm going to rewrite this function just up at the top of the board, and then we're going to play with that function a little bit. Okay, let me simplify this a little bit as I rewrite it. So we have s of r equals 2 pi r squared plus, you can see the pi's cancel out, one of the r's cancel out, and we end up with 2v over r. This is the thing we want to minimize. Okay. So how do we minimize this? Well, we start by maybe establishing its domain. So for what values of r is this function defined? It's actually defined for all values of r except r equals 0. But because r refers to the radius of a can, we're also going to insist that that not be negative, because a can with a negative radius doesn't really make sense. So we want to minimize this. On the interval from 0 to infinity. Now, a can of radius, I don't know, 0.1 millimeters also doesn't make too much sense, but it at least makes a kind of metaphysical sense, unlike a can of radius -5 centimeters. So we want to minimize this on this radius, on this domain. So let's take the derivative. And at this point, this is just a standard problem that we know how to solve. S prime of r is equal to 4 pi r, using the power rule. And then differentiating the second term, I get 2v over r squared, and negative up front. I want to find out when this is equal to 0. So I'm going to factor it. I'm going to pull out a 2, because both terms have a 2. And I'm also going to pull out an r squared. And so what I'm left with is 2 pi r cubed, and from this term, just a v. And we're looking for critical points. So, where is this thing equal to 0? Well, this first term is never equal to 0 on this domain. In fact, it's never equal to 0 on any domain. But this term could be equal to 0. So this vanishes exactly when 2 pi r cubed minus v is equal to 0. In other words, when r cubed is equal to v over 2 pi. But what is v? What is v? Well, v is the volume of the can, and we know that that's given by pi r squared h. And so we have this relationship between r and h. So our derivative vanishes when, and now I'm just going to solve for r, when r is equal to h over 2. So this is our critical point, and we hope it's our minimum. So let's check. So is S of r minimized? Okay. Let's draw a table. Let's draw a table like we always do when we're curve sketching, where we're going to take our domain and split it up with this critical point. So I want to know what happens when r is between 0 and h over 2, and what happens when r is between h over 2 and infinity. In particular, I want to know what is the sign of S prime of r, and that'll tell me if S of r is increasing or decreasing. Okay, so when r is small, here's my derivative. This is always going to be positive, but when r is small, this term is going to be quite small. And so this term is going to be a negative, right? Because this term is going to be dominated by that constant. So S prime of r is going to be negative. And when r is big, when r is really, really big, say, this is still positive. And now this term is huge. And so this term dominates this term. And so on the second interval from h over 2 to infinity, the derivative is positive. And so the function goes from decreasing to increasing. And this tells us that our original function has a local minimum. In fact, a global minimum, since our original function is continuous on this domain. It tells us that it has a global minimum at r equals h over 2. Just write that down. And that's really it. I mean, that's the answer that we're looking for. The most economical shape is one where the radius is half the height. So if I draw it, it looks side-on like a square. Now this is the answer to the question, But there are a few ways that we could push it in different directions. So first we could confirm whether we did all of this mathematics right by answering the second question, or answering the question using the second approach. Given a fixed surface area, do we maximize the volume with a can of this shape? That ought to be so. And also, now this is a question with kind of real physical implications. And I'll point out, though this is not strictly mathematical, that most cans do not look like this. Most cans are taller than they are wide. And so we ought to ask ourselves, what is it about the assumptions that we've made that isn't quite accurate? What are we missing? It might have something to do with the cost of joining the tops and bottoms of the cans to the sides. It might have something to do with the thickness of the top and bottom, but we're missing something. And that's an interesting question.